Okay, let's get started. All right, you want to do this recurrence on your own and then tell me what the answer is? What is the solution for this? Don't look at the slides because this is from last week, Tuesday. How does a recursion tree look like this? Look for this recursion. What's the shape of the tree? A straight path, right? Why only one child, right? Okay, so let's draw it. So I'll give you n, only one child, square root n. What is the next one? N to the square root of square root n, right? That is 1 to the 1/4. Okay, let me put the base case. T of 1 is 1. Okay. Okay, at some point you reach 1. There has to be some floor here, but don't worry about that. So what is the work you do here? 1, 1, 1. So what is the total work? It's the same as the depth of this recursion, right? So really, what is the depth of the recursion here? Don't guess, do some math, right? Right? Can you figure out when? So it's an interesting question, no? If I take n and cut down the problem size by half, like in merge sort, n goes to n over 2, then you cut down again by half, n over 4. How long does that process take before we stop? That's the depth of the recursion, right? So what is that? If I go down by a constant factor, what is that? The depth of the recursion? Log of n, right? Log n is, you should think about log n as how long will it take for me to get to a constant if I cut the problem size by half each step, or 1/4. Then it will log base 4 instead of log base 2, right? Here, I'm not cutting the problem by half. I'm not cutting in the sense that I'm making it square root n. It's even smaller than half, right? So now we're interested in asking, if I take the problem of size n and make it square root n, and then again we make it another square root of that, it is going faster, right? It's going down faster. So we want to know, what is that? How many steps will I take as a function of n? Well, it should be definitely no more than log n, right? Because we are going down faster than constant factor. So the question is, what is this function, right? Okay. So is it something that we can understand in what we are? No, yeah. What is it, right? Sorry? No, you raised your hand, so I thought you knew that. So it's log of n, right? We'll see why it is the case. But see, now you should have that understanding that, I have a better way of thinking about log of n other than it's just a function, right? When you think about recurrences, I say, if I take a problem of size n and I make it square root and then I again make it another square root, that is log of n, right? So that's even smaller than log n, right? It is, okay? So how do you figure that out, right? It's actually very elementary, right? What is this? It is n to the 1, this is n to the half, this is n to the 1/4, right? What's the next step? N to the 1/8, right? Yeah. So the exponent is going down by half, right? Okay. So basically we say, okay, we don't know how many steps, so it will be about, so we can say, it is, if it is k steps, after k steps, the size of the problem is n to the 1 over 2 to the k, right? Okay, we want to know when that becomes a constant, right? So I'll put 2 here because we're going to take logarithms, right? And if it is 1, then you get into an infinite loop. And so you take the base case as 2 for simplicity, otherwise of the log, right? And so you say, okay, now what should I do? I need to find k, right? Okay. So I take logs on both sides. So what do I get? 1 over 2 to the k log n is basically 1, right? I'm trying to find out what is the value of k before I get to a constant. Yeah? Agreed? Okay, so then that gives 2 to the k is log n, so k must be what? Okay? Agreed? Yeah? So depth of the recursion is log n, and the work is basically the depth of the recursion, right? Yeah? Okay, what happens if I change the square root n to the 1/4? What do you think will happen? Sorry? Suppose I say, instead of t of n is t of square root n plus 1, it is t of n to the 1/4 plus 1. Yeah? Yeah, it will still be log of n, but the base will change now. Okay? It will become 1 over 4 to the k, right? The problem of after k steps will be n to the 1 over 4 to the k, right? So the basic algebra is still the same, right? Yeah? 2 on the thing is only because if you go to 1, what happens is that you get into, if you take t of, if you put t of square root of n as, is the same as 1, right? But t of 1 is 1, so you'll get into infinite loop if you don't stop at 2. Okay, my base case really should be at 2. Okay, so this recurrence doesn't make sense for n equal to 1. Why is that? You will get t of 1 is t of 1 plus 1, right? But so that's not making the problem smaller. Okay, so you have to, I mean, this is not defined for n equal to 1. The base case should be at 2. Okay, so technically we should write floor of square root of n, right, to make it more formal if you are staying in integers. Okay, so if you go all the way to 1, then t of 1 is t of 1 plus 1, right? That means that we are not really recursing, we are not making the problem smaller. So the base case should be at 2, not 1. Yeah, that's why I put 2. Yeah, all right. As you can see, otherwise if I put 1, I'll get 0 and I'll get infinity here. The math still works out. You'll get, wait a second, something is wrong, you should realize, right? Okay, okay. So I hope you have a better understanding of what log is now, right? Because I mean log n is, right? Okay. Okay. Now what about this? So now you know the depth of recursion. Okay, try to solve this now. Okay, I'll give you a couple of minutes. Draw the recursion tree while I get my pointer. And just add up all the work. Okay. So the interesting thing about recurrence is that the number of children is not fixed, right? It's also a function of n, right? Okay, that's so just to get people oriented, this is so there is a problem of size n. How many children do I create? Square root of n, right? Okay, that's what it says, no? This many children of size square root of n, right? And then the work I do to put them together is n. Okay, so I have many children. So this is a huge number of children. Okay, it depends on n. Each of size square root of n, and the work I do is n, right? And this guy, how many children is he going to have? Yeah, n to the 1/4 children, each of size n to the 1/4, right? So the tree starts out very bushy and starts getting little less bushy as it goes along, right? I mean, each, right, that it's not even a constant, right? But there is no magic to it, it's the same thing. It's just basic algebra, right? Okay, now I'm going to not draw as many because, okay, but let's see, what is the work we do here? Okay, can you tell me how much work we do at, so we need to add up all this work, right? Yeah? Okay, what is the work we do at this level? It is n. Can we add up all the work at this level? How much work do we do? Yeah, how many children are there? Square root n. How much work do they do? Square root n. Total work here is, so n, and then you can guess the pattern, right? The next level also will be n. Okay, now what is the total work? How many levels are there? Yeah, we just figured out, right, that the depth of the recursion is log n, right? Why? Because if you go down as square root n, the depth is log n. Yeah? Okay? So the number of levels, where do you stop? I should again say t of 2 is 1. You stop at, so the depth of the recursion we already figured out from the previous thing was log n. Right? Because along each branch, n square root n to the 1/4, how long will you go? You will go log n, right? So the total work is n times log n. Yeah? Is that all right? Okay? That's it. Okay. So that is n. Okay, what about this? This looks different in some other way, right? Does it look like the merge sort recurrence? Well, sort of, I say. Okay, so in merge sort, what do? We take the array and split it into two arrays of size n over 2, right? But I say, I'm a little, lazy or something, and I say, I stop at n over 4 and 3n over 4. I make it a little lopsided. Okay, so what is lopsided? I say, I'm not going to break them exactly into half. I'm going to make one guy 3/4, one guy 1/4, right? Why does that happen? Why do we think, obviously that doesn't seem to be the right thing to do, but when you do like quick sort or something and you do, if you pick a random pivot, maybe it won't be exactly balanced, okay? So it makes sense that, maybe, one side is going to be not too small, but it is going to be a little bit off, right? Not exactly half. Now we want to understand, get a feel for it. Okay, if I don't split it exactly into half, does the running time still stay n log n roughly, or does it somehow become bizarre? Okay, right? We want to understand it. How robust is our analysis, and so that we'd say, that's safe to do, right? Maybe in some algorithm you say, some reason I cannot break it into exactly half, but maybe I can break it a little bit lopsided way, and what will it do to the running time, right? We want to know the sensitivity of our analysis so that we can use it in the design as well. So what do you think will happen? What is your guess? Right? Yeah, so it look a little bit lopsided, no, the tree, okay? So it's a bit harder to understand, but let's see, we should develop some tools to make sense of this. So, okay, so look, okay, one side is a bit lopsided. So what does it mean? Okay, so it looks like this, right? Okay, now let's keep going, because what happens to this guy? N over 16, and this guy is 3n over 16. Okay, now this like, okay, what am I going to do now? Okay, this is 3n over 16, and this is 9n over 16, right? Okay, and so you can see that this guy the tree will look like this, right? In the sense that this leaf will end earlier than this leaf, right? Yeah, so it's like, okay, now it's a little bit harder to understand this, right? But let's do some basic things. So so we'll imagine that, okay, this is not going to happen anytime soon if n is large, so let's see roughly what is going on, right? Just like in the past, we'll say, what is the work we do at each level? Let's understand that. Okay, it is n at the top level. What is the next level? Here we put n over 4. What about here? 3n over 4, right? So what is the work we do at this level? Again n, right? Yeah, total work we do at that level is also n. So we say, aha, n. Oh, that's good. What is the work we do at the next level? It also will be n. If you add up, you see that the work we do is the same as the sum of the problem sizes, right? Yeah? Because of this function is n, so the work we do is the sum of the problem sizes, and that's not changing, right? The sum of the problem sizes, the array size is staying the same, the total sum of the arrays. Okay, so good. So we have a good understanding that, oh, the work at each level is n, but now we are a bit unhappy because we don't know how to add it up, because we'll say, at some point this will stop and then n will start decreasing, right? Okay, how do we count the total work? Okay, so we can't count it exactly, right? Because we can try to count it exactly, but it requires a lot more work to find out precisely. It's not as clean as the thing. But then we have to remember what Einstein said, right? Okay, you have to simplify, but not too simple, right? You have to kind of get at the right thing by saying, I'm not interested in the exact answer, I'm interested in the asymptotic answer, right? So what does it mean? We try to find a lower and upper bound on the work, and if they're within a constant factor of each other, we say, that's all I need, I'm happy, right? If they're not within a constant factor of each other, and say, I don't know the asymptotics very well, I should probe further, right? Okay, so can we say how much is the upper bound on the work we do? If it is n per level, what is the maximum depth of this recursion? The depth of, so this guy will be the deeper node, right? So what is the depth of that leaf? Can we calculate that exactly? Log base, yeah, it is log base 4 over 3n, right? Why? Because I'm cutting down by 3/4, right? So if I start with n, then I go to 3/4 n, then it 3/4 square n, 3/4 cube n. When will I stop? It is 3/4 to the k n should be constant, right? About 2, right? Or some constant. So that is log of n to base 4/3. Yeah? Instead of 2, it is 4/3. So it's a little longer than log base 2, right? But only by constant factor, right? Yeah? So this depth is log n to base 4/3. Okay, what about this depth? Sorry? Yeah, this depth is log n to base 4, right? It is shorter than log n to base 2, right? Because this we are cutting down faster, right? Yeah? Okay, so my claim is the total work is at most n times log n to base 4/3 and is at least log n, n times log n to base 4. Yeah? Because, till this level, I'm going to spend n, right? So the work I do is at least n times log n to base 4, no more than log n times log n to base 4/3. Okay? That's it. Okay? So are they within a constant factor of each other? Yes, right? Because log n to base 4 is what? Log n over log 4. So it is log n by 2 basically, right? And log n to base 4/3 is what? Log n divided by log 4/3, which is some constant, right? So we have roughly within a constant factor, the work is n log n, right? So that's all we want. We want the asymptotic bound, right? So we got n log n. Do we know precisely, is it 5n log n, 3n log n? No, but it's okay, right? We only want to know, is it n log n or is it n log cube n, right? Asymptotically it's n log n, right? So that's it. That's the easy way of bounding things. And sometimes when you do upper and lower bounds, they don't match. Upper bound will say n log n, lower bound will say n. Then clearly we don't have a good understanding, right? It is n log n. Is the n log n the right answer? Is n the right answer if our upper bounds are not asymptotically matching, right? So then we have to do more work. But here we didn't have to do more work because it happened to be easy enough, right? But now we have a design principle, right? We say, any merge sort type recurrence, as long as these two are within a constant factor of each other, it will be roughly n log n, right? So then we understand a little bit better, okay, it is not so critical that the array is exactly balanced. Yeah, that's a lesson we draw from the design point of view. Okay, So that's called lopsided recurrence. And so let me ask one more question to kind of, because we are going to use it in our sorry. In the lecture, where is it? Okay. So here is the thing. Suppose T of n is T of 3n over 4 plus n, and T of 1 is 1. What do you think the answer to this is? Okay, so let's draw, right? Okay. Only one child though, right? Right? Okay, n, 3n over 4. So what is this total work we do, you think? Sorry? Right. So it is n plus 3n over 4, 9n over 16, right? Oh, that's an upper bound, but that's a very weak upper bound, right? Sure, it is an upper bound. We won't do more than n square, but can you put a better upper bound? How many levels are there here? What is the depth of the recursion? Log n to base 4/3, right? Okay. Just like we saw the earlier, right? So it's no more than n times log n to base 4/3, right? It's better than n square, right? They're not n levels, they're only many fewer levels than n levels because we're going down by constant factor. But can we do even better? Why? We want to add this up, right? But this is a geometric series, no? N plus 3n over 4, right? So it's n times 1 plus 3/4 plus 3/4 square plus 3/4 cube plus blah blah blah. Even if you go to infinity, it still converges to a constant. Yeah? So the total work here is linear, constant times n. So it's very important, right? So what this says is that if you have a problem where you can cut down the size of the problem by a constant factor, one problem, right? You recurse on one problem with this a constant factor less than the original problem, and you still spend linear time, the total time is still going to be linear. Is it okay? So it is saying that whenever you have a problem where you can start with this problem of size n, cut the problem size to a constant factor less and spend linear time, the total running time will be linear, right? It's like saying n plus n half, half n plus 1/4 n, right? It's just that the constant is different. Yeah, that gives an upper bound, but here it is going down dramatically, right? The work is going down dramatically. If you put n here, clearly it's an upper bound, but it is not n, it is 3n over 4, right? It's going down by constant factor. Then it's going down by another constant factor. So the total work is n plus 3n over 4 plus 9n over 16 all the way to 1, right? But the meaning of this recurrence is when the problem size is n, it is n. When the problem size is 3n over 4, it is 3n over 4. Right? When you say, what is the meaning of this recurrence? We are telling us for a given n, what do we do? We spend n time, but we cut down the problem size by 3n over 4. This becomes the new n for the new problem, no? Yeah, right? Okay. Yeah, so that will converge to a constant, right? Yeah? Okay, so that's recurrences so that we can actually do some algorithms now, right? Because the recurrences are there to help us not only analyze but design algorithms, and that's very important. It's not just that recurrences are there later, right? So let's see. So we are doing divide and conquer, and I did this in my very first lecture to tell you that algorithms are funky, right? Let's go back to what I try to teach my son, and he doesn't try to listen to me, right? How to do multiplication, right? The grade school way, right? So I have two long, right, numbers, and I want to multiply. How are we taught to multiply? We say, okay, and we are, here you can't say, multiplication is constant, right? My computer can do it in constant time. That doesn't make sense. As a problem, we have to, what is our elementary operation here? Digit multiplication, right? That's one step, right? All right. Okay, we know the multiplication, hopefully, right? So if you have two n-digit numbers, how long will it take? N square time, right? Why, you multiply this, you get an n-digit number, then you get another n-digit number, you get another, and then we have to add all of them up, right? So it's n square. Okay, can we do faster than n square? Right? You can do dramatically faster than n square, actually. Okay? You can do it roughly in n log n time. Okay? It's not obvious how to do it. Okay? I can't teach you now because you have to learn, it relies on fast Fourier transform, right? But I'll teach you today the first step. Somebody figured out that you can actually beat n square, right? Significantly. And that's the seed of the idea. And to do that, we need to go do some complex numbers. You see, there are no complex numbers in the definition of multiplication, but somehow thinking about complex numbers is important to actually solve this problem much faster. Okay, this goes back to another famous man, Gauss, right? So let's think about two complex numbers, right? A plus bi, the imaginary part is this, and c plus di. How will we multiply them? Yeah, this is the definition, no? You say, okay, a times c plus, bi times di is bd, I square, that is minus 1. So it is ac minus bd plus ad plus bc times I, right? Yeah? It doesn't matter if you know complex number or not, that's the definition, okay. Okay, you see, if you ask me to do this, how many multiplications do I need? 4 multiplications, right? You say, aha, I have to multiply a and c, okay. We do know somehow that addition is a little easier than multiplication, no? Yeah, we just saw. If I want to add two n-digit numbers, I take n time, but if I want to multiply two n-digit numbers, I take n square time, right? So it's in our interest to cut down the number of multiplications, right? So I ask you, can you do it with less than 4 multiplications? Okay. Can you do this with less than 4 multiplications? Okay. It's like, why can you do that, right? This is the definition, right? Okay. It seems like, okay. You can. So that's what Gauss did, right? And so he said, aha, you're a little clever. He noticed something. He said, wait a second. I don't need to know each of these things. I only know this. I want to know only this, right? Finally, I don't want to know AC, BD, AD, BC because that's not my goal, right? I want to know only these two things in the end, right? AC minus BD is one number and AD plus BC is one number, right? I don't care about the intermediate things, right? Okay. So he said, okay. So I won't compute all of them separately. I'm going to compute A plus B times C plus D and AC and BD, right? So 3 multiplications, right? Okay, only 3 multiplications. And then I say, what is AC minus BD? Well, it is, or AD plus BC is A plus B times C plus D minus AC minus BD. Right? Once I have these 3 products, I can get both of them. Okay? You see that? Yeah. Who cares? 3 versus 4, right? Yeah? But it is clever, no? Yeah? Agreed? Do you realize it or no? Do I have to spell it out? Yeah? Okay, good. So what is the point of this? Okay, there is a point, right? Okay, now let's go back to our multiplication and see if we can speed it up. Okay. Okay, first, we don't know, right? We are in the land of divide and conquer, right? We are exploring this technique. So suddenly we learn divide and conquer, and maybe we should try to use divide and conquer to solve multiplication faster. So what is the natural thing if you want to apply divide and conquer to multiplication? Right? I want to multiply two n-digit numbers. How would I apply divide and conquer, right? So I want to cut the problem in half, say, the most natural strategy, right? Yeah. So you have, right? You cut both numbers into half. I mean, you take a big n-digit number, cut it into n over 2-digit number, n over 2-digit number. Well, what does it mean to cut it into n over 2-digit number? You have to put zeros there, right? Yeah. But zeros are easy, right? Multiplying 100 by 100 is easy, no? Yeah, because the zeros can be taken care of. Okay, so the natural thing is to say, okay, suppose it's easier to see with an example. If I want to multiply 1, 2, 3, 4 by 5, 6, 7, 8, and we say we want to use divide and conquer simply because we are playing with this technique, what would you do? You say, okay, I am going to split this 1, 2, 3, 4 into 1, 2, 0, 0 plus 34, right? Okay, right? Does it make sense what I did? I just said, oh, it is 100 times 12 plus 34, that is just 1200 plus 34 times, okay, multiplying these hundreds is easy, so I have reduced the problem to multiplying, instead of 4-digit numbers, I am multiplying now 2-digit numbers, right? Yeah? Agreed? Okay, how many multiplications do I need? I need to multiply, so to compute the answer, I need to multiply 12 and 78, 34 and 56, and 34 and 78, right? Agreed? No, I also have to multiply 12 times 56. So how many multiplications of n over 2-digit numbers do I need? 4 of them, right? Okay, so I mean, is this making sense at all or no? Okay, okay. So I have an n-digit number, right? Xn minus 1, Xn minus 2, long n-digit number. Okay. I want to multiply it with Yn minus 1, Yn minus 2, Y0, right? Okay. So I say, okay, I'm going to think of this number as two n over 2-digit numbers, right? Yeah. Okay, and so that I can solve the problem for n using multiplication with n over 2-digit numbers, right? Yeah? Okay, but how will I do that? I mean, it's a basic thing, right? You say, write this as this number, let's call it A1, and this is A2, this is B1, and this is B2, right? Okay, so you write it as 10 to the n over 2 A1 plus A2 is this number, no? This number is 10 to the n over 2 A1 plus A2, right? Sorry, because there are n digits here. You put n over 2 zeros, right? Yeah? Okay? So this times, 10 to the n over 2 B1 plus B2, right? Yeah? Okay, now what is this? Yeah, is 10 to the n, you have A1, you have to multiply A1 B1, right? That's 10 to the n A1 B1 plus A2 B2 plus 10 to the n over 2 times A1 B2 plus A2 B1, right? Yeah? Okay, so if you write it recursively, what did we do? We took to multiply two n-digit numbers. How many multiplications did we have to do? 4 multiplications of n over 2 numbers, right? And then what do we need to do? We need to add them up, right? The results. Okay? Agreed? So what is the recurrence you get, right? Does it make sense what we did? Yeah? Okay. So what is the recurrence you get? You get to multiply, so the problem size is n. We get 4t of n over 2 plus O of n, right? Is it okay? So once you compute the answers to this 4 multiplications, we can add them up in n time, no? Because there are only 4 numbers. Yeah? And their size is also only O of n, right? Is this okay? The recurrence is okay? Is the algorithm okay and the recurrence okay? Yeah? Yeah. Oh, okay, let's do it, right? Do you want to do it abstractly or concretely? Okay. Okay, so see, I want to multiply x, y, right? Okay. Remember, x and y have n digits. Okay, I split the x into the top L over 2 digits is only n over 2, right? Let's call that number xl, where I strip out the zeros. Okay, but if I want to put really the number, what is x? X is 10 to the n over 2 xl plus xr, right? Yeah, I put 0, okay, and y is 10 to the n over 2 yl plus yr. Oh, so look at the formula. It is if I did this, then what is the product of this? 10 to the n times xl yl plus 10 to the n over 2 xl yr plus xr yl plus xr yr. That's it, right? So, but these numbers, this product is only, we are multiplying two n over 2 digit numbers. So this is one thing I need this, I need this, I need that, no? Right, but all of them are multiplying two n over 2 digit numbers. So I've cut down the problem of size n into 4 problems of size n over 2, and then how do I put them together? I have to add them all up, right? But adding is a linear time, no? 4 additions, so that's the recurrence. Yeah? Yeah. Yeah. So T of n is 4 T of n over 2. Oh, because I'm adding, so this is just a shift, right? I can add n zeros to it. I add n zeros to n over 2 zeros to this. If I have this sum, so remember this, how many digits does this number have? Only n basically. I mean 2n maybe, right? So I'm adding 4 numbers of length about n each, so it should take about n time. No, adding takes only n time. Yeah. Is this recurrence okay? Oh, sorry. Yeah? Sorry? Adding 2 n digit numbers takes n time, no? Yeah? Yeah, any question of the recurrence? Yeah? N time. Yeah, n time, yeah. That's why I put O of n, maybe put 6n if you are happy, right? Yeah, right? Is it okay? Yeah? What is the solution to the recurrence? Yeah, is it going to be n square, n cube, n 100? Why? I don't see any algebra. I don't see any algebra. How did you think it is n log n? You got to do the math. You can't do it like that. You guys are not experienced enough to say pull it out like that. Okay? Why are you asking me? Do it. So I am the one asking you, you're not asking me. So I'm saying figure it out only because it is important for you to do it. I know the answer. Right? But it is more than the height, no? There is a method to it, no? Not everything is n log n. We saw it already. It's one is n log n, something is n square, something is n cube. How do we do it? We just have to do the math. There is no other thing. Exactly. That's the point. You have to figure it out by doing the math. Okay? There is no other way. I'm sorry. Right? Okay? I did it too. Okay? So you got to do it. That's how you learn, right? How does the 4 affect? By drawing the tree with 4 leaves and 4 children instead of 2. Right? And adding up things, right? It's the same formula, but same idea, the method. But small things can make different things, no? Where is the paper? Okay, see, if you guys are so good that you can do it in your head, I'll give it to you, right? But, you're not yet, so you got to do it, right? Don't look at me, look at your paper. Okay. All right. We have to do more interesting, more difficult stuff. So it's sorry. Oh, yeah, 2n in the first level. He says, oh, it's okay, good. What happens in the next level? 4n. It seems it's going up and it's not going down, right? Okay. So what is going to happen in the next level? 8n. Okay, is the work increasing or decreasing? It's going up and up and up, right? So when will it stop? What is the work? Will it go to infinity? It can't go to infinity, right? Hopefully, right? We stop. When do we stop? After k steps, what is the work we are going to do? No, total work at level k. First level is n, second level is 2n, he said. Third level is 8n. After k levels, what do you get? 2 to the k times n you'll get, right? After k levels, right? And third level is 8n, it's 2 cubed times n. Fourth level will be 16n. And the next level will be, so it's doubling at each level, no? Okay? Yeah, 2 raised to k. Okay. No, I mean, no, it's not, you can't treat it as a constant because it's going and going, right? No, but see, so we have to add up the work, right? It's n plus 2n plus 8n plus 16n. Where do we stop? No, the depth, right? Because the last level is at log n to base 2. So it is 2 to the log n to base 2 times n. What is that? No. 2 to the log n is what? N, right? Okay, so it's n square at the last level. So it is n plus 2n plus 4n plus 8n all the way to n square. So it's a geometric series, but it's stopping at, growing and stopping at n square. So the total work will be n square. Okay? We got nothing out of it. Exactly. So we didn't succeed. Okay? Okay. So because we didn't rely on Gauss's trick yet. Okay? Remember, we did 4 multiplications, no? To multiply these 2 n-digit numbers, we did 4 multiplications of n by 2. But Gauss told us in some settings you can reduce it to 3. That's good, no? If you take 4 to 3, maybe in the recursion it will help us, right? So can we do it with 3 multiplications instead of 4 using Gauss's idea? See, remember, ultimately what do we want? We don't want each of these individual products, right? What do we want? We want XLYL, we want XRYR, okay? But we only want XLYR plus XRYL, okay? The sum is what we want, right? Can we get that without doing these 2 multiplications? Okay? And just using Gauss's idea, you can, and that's what you can do. Instead of multiplying XLYR separately and XRYL separately, you compute XL plus XR times YL plus YR in addition to XLYL and XRYR. Suppose you did that. How many multiplications is that? 3 multiplications. But now you can get XLYR plus XRYL as the product of this minus XLYL and XRYR. Okay? Same idea, right? Roughly the same idea, right? So now instead of doing 4 multiplications, we are only doing 3 multiplications of size n over 2 and some additions and subtractions, right? Which all take only O of n time. Okay? So what does it do to the recurrence? What is the recurrence now? T of n is what? Three of t, right? Yeah? Okay, now what does it do to the solution? Okay? Okay, we again have to do the algebra. There is no solution to this other than doing the algebra. Okay, since I am going to be running out of time, I'll tell you the answer and you'll figure it out later. Okay, it is n to the log 3 to base 2 now. Okay, see, the depth is again log n, right? The depth is log n because we are cutting down the problem size by half at each step. But the work is not 2n at each step. What is the work at the second level? It is 3n over 2, right? Not 2n, right? It's 3n over 2. What is the next level? It is 3 over 2 times 3 over 2 times n. So it is 3 over 2 square. So at the last level, it is 3 over 2 to the raised to the log n to base 2 times n, right? It is not 2 to the raised to log n, but 3 over 2 raised to the log n. Okay? So if it is 2 to the log n, it is n, right? But if it is 3 over 2 to the log n to base 2, what is it? It is n to the, okay, this is what you get. It is n to the log 3 to base 2 minus, it is n log 3 to base 2 minus 1 you'll get. And so it's n times that, so you'll get n to the 1.585. Okay? It's just a solution to the recurrence, right? So we beat n square, no? So we could do better than what we learned in grade school. Yeah? But it was not easy, no? It was not easy, right? You had to learn this trick, right? This seems like a bizarre trick, right? Okay, but that's why algorithms are not obvious, okay? This is not at all an obvious algorithm. Why would you think that this simple trick will give you this analysis, right? Okay, so it is not obvious. In fact, Karatsuba did this, in the 1940s or 50s, right? But, whenever you see something bizarre like this, you must say, there's something deeper going on, right? It can't be that some simple trick is doing some funky thing and we are done with it, right? So people said, wait a second, something interesting is going on. And, it only took many years later, but people then developed this fast Fourier transform, complex numbers come into the picture, and the best running time right now to multiply two n-digit numbers is n log n times 2 to the O of log star n, okay? And it's conjecture that you can do it in n log n time. Okay, it's way, way, way faster than n square, okay? It's a beautiful algorithm, okay? It is not at all obvious. You need to understand a little bit of polynomials, right? So the point of this lecture is, first, of course, divide and conquer gave you already an improvement over n square, right? First, non-trivial significant improvement over n square, which is the obvious method. So then suddenly you should start thinking, multiplication is tricky, right? Something interesting is going on, right? But the final answer is still not known, and we don't even know whether actually we can get n log n time, right? But yeah. No, yeah, to some extent, yeah. No, it's not like that. What I'm trying to say is that you see, the computation is complex. Okay, we should respect computation in the sense that it is not obvious what to do, right? So it is not computations. It's not the multiplications problem that we don't want to do it, right? Our job is to figure out the best algorithm, right? So sometimes, that requires learning more math. There's no solution to it, right? And this is not difficult math, no? This is not difficult math in my view, right? Solving these recurrences is not difficult once you figure out what we're trying to do, right? They're just elementary operations, but you have to get comfortable with it, right? Having a comfort with recurrences is necessary to design, not just to analyze. That's what I'm trying to make a point of, right? Okay, you have to get a feel for like, okay, that also would work. Okay, questions? I hope you remember that multiplication itself is not obvious, okay? How to do the best algorithm for multiplication is not obvious, right? That's the point. All right? Okay. So I want to stress that point again because we'll use that in this very simple problem, right? That you all should find it interesting. So I give you an array, right? And we all know how to sort. It takes n log n time, right? Okay. But I don't want to sort, right? I want to find, for example, I tell you, I want to find the smallest element in the array. Do you need to sort? You don't need to sort to find the smallest element in the array, right? Yeah? Okay, I say you want to find the largest element in the array. Do you need to sort? No, right? What about the second smallest element in the array? Why not? Right? You can do 2n time, right? So you find the smallest element and then remove it and find the next smallest element, right? Okay, now I say find the 100th smallest element in the array. Right? Seems simple enough, right? Well, you could do the algorithm we just saw, right? You know, find first smallest, remove it, second smallest, remove it, third small. How long does it take? 100 times in. That's not looking so good, no? Well, you know, it's okay. If you want to be more careful, it is n plus n minus 1 plus n minus 2 up to n minus 100, no? Unless, okay, you can do sorting too, right? Okay. Sorry? No, it's not sorted. The array is not sorted. Let's go. We are going to get there. Okay. Okay. Now I want to find, you know, not 100 smallest element, but I want you to find the median of the array. What is the median of the array? It's the guy in the middle of the array, right? Okay. Okay. No, middle of the array when you sort it. Not, remember, my array is not sorted. Okay. See, this is the unsorted array. This is the sort of the array, right? Okay. So where is the median here? Well, what is the median? Okay, this guy, 14 is the median. But he's here, no, in the unsorted array. Okay. Okay, is the problem clear? So the more general problem here is, I give you an unsorted array and I want to find an element with rank j. So what is an element of rank j? We sort the array and you look at the position of an element in the sorted version and that is its rank. Okay, what is the rank of the smallest element? 1. What is the rank of the largest element? So what is the rank of the median? Okay, if it is, it's n over 2, right? You know, you have to be careful because if the array has even size, what is the median, right? By convention, we will call the median is the n plus 1 over 2 floor as a median. So if the array is of odd size, then it's the middle guy, right? If the array has 7 elements, then we know what is the median, right? It is a fourth element. Yeah? So this formula will be okay, right? If n is 7, it will be 8 over 2, it will be 4. But if it is the array is of size 6, what is the median? What is the rank of the median? Should it be 3 or should it be 4? So this says, you know, let's choose 3. Okay? It's just a convention. You can call it 3 or 4, right? Okay. So now the question is, my problem is not to, I give you the unsorted array and I tell you I want to find the median or I want to find the 150th smallest element. So I want to find the element with rank 150. Obviously you can easily do it by sorting, right? You sort the array in n log n time, any rank you can get, right? Yeah? So the question is, do you need to sort? Can you solve this problem in better than n log n time? Clearly you have to spend n time, right? You have to look at the array, right? Can you do it in better than n log n time, right? This is what keeps theory people up at night, right? Right? Can they do it? Can we do it? Right? Yeah? Sorry? No, you are saying you can do sorting better than n log n time? No, I mean, if you, yeah? I mean, of course, if you can sort in linear time, you can, but do you know any algorithm for sorting in better than n log n time? Unless you're using radix sort or something. No, these numbers, don't think of them as small, they're big, right? You can't like bucket them, right? Otherwise, yeah. Yeah? No, there are no same elements, they're all distinct. Yeah, just for simplicity. It's not important, but okay, yeah. Okay? The surprising thing is you can do it in linear time. Okay? Alright? So if I give you an unsorted array and I give you any rank j, right, or just think of finding the median, you can do it in n time, I mean constant times n time. Okay? Okay? So that's what we're going towards, right? So it's a very nice result, right? It's not very practical in many ways, but right? The fact that you can do it in linear time is very nice. Yeah? Okay? So let's do it. Okay. How do we do it? For simplicity, we are going to assume all the numbers are distinct. Otherwise, you'll get a little confused. Yeah? Okay, it's not important. Okay. So we already saw sorting takes n log n time. You can find all the ranks. The question is, do we need to sort, right? Okay, we saw that if j is very small, like j is 1 or 2, we can do it in j n time, right? If you want a smallest element, you can do it in j n time. Okay, here is a divide and conquer approach based on quick sort, right? Okay, it's called quick select, which was developed at the same time as quick sort. So you choose a pivot, however you want, and you split the array into two arrays, the one smaller than the pivot and the one's bigger than the pivot. Okay, what happens in quick sort? You have to sort both sides, no? But I'm not interested in sorting. I only want to find the rank j element, right? So where should the rank j element be once I figure out how to, once I pivot? Okay, so let's do an example. Okay, so easier. So I want to find, what rank do you want to find? Okay, you choose j. This is the array. How many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you want to find the rank 4th element, for example, or whatever? Like rank, say j is 4. Okay, now pick a pivot for me. Okay, because the algorithms implemented will do always the first one, we can pivot using 16 if you want, right? Just, yeah, that's the algorithm that's implemented in C or something, right? The first element is used as a pivot. So if you use 16 as a pivot, what happens? What does the array split into? Yeah, so it will split like this, right? Roughly 14, 12, 5, 3, 11. Then what happens? 16, then whatever, right? 20, 34, 19, right? Am I right? Did I make a mistake? Yeah? Okay. So I split the array into, I use 16 as a pivot, right? So I split the array into all the numbers smaller than 16 and all the numbers bigger than 16, right? Yeah? Sorry? I don't care really. I didn't tell you how exactly I'm implementing, right? All it does is it splits it into two pieces, right? Yeah. Maybe if you talk of a specific implementation, probably 34 will come before 20, right? Okay. Okay. But I'm interested in the rank 4 element. Where is it? It should be on this side, no? Yeah. Agreed. So because when I pivot with 16, what do I learn from that? I know the rank of 16, no? What is the rank of 16? It is 6, right? I know that, and okay. So clearly my rank 4 element should be on this half of the array, right? Yeah. So I can discard this and recurse on this side and looking for rank 4 element in this array. Okay, but if I want to rank 6, am I done? If I want rank 6 element, I'm done because I found 16 is rank 6, right? Okay, if my pivot's rank happens to be the rank I want, I'm done, right? Okay, but suppose I want to find the 8th ranked element, what should I do? I should go and look in this side, right? Yeah? What should I recurse on? What rank should I look for in this side? Remember my j was 8, right? If my j was 8, I have to recurse on this side, right? But what rank element should I find in this array? 2, right? Because I already found 6 elements which are smaller than that. I have to look in this array with rank 2. Is the algorithm clear now? Recursive algorithm? You start with the unsorted array, pick a pivot, see what happens. If the rank of the pivot is exactly what I am looking for, I am done, right? Yeah. If not, I have to either recurse on the left side or on the right side, depending on whether j is bigger than the rank of the element I found or it is less than that. Is that clear, the algorithm? Okay. How long will this algorithm take? What is the difference between quicksort and this? I am recursing on only one side, no? Because I am not interested in sorting, I am interested in. Okay, how long will this take? It's based on the pivot, no? Yeah? Okay, suppose we get lucky and every time the pivot is somewhere in the middle. What does it mean? That means that both sides are only about no bigger than 3n/4. Suppose we get lucky. Somehow we are in that good state. What does the recurrence look like if we happen to make the arrays, the pivot is somewhere nice, it's not too bad. How much time do I spend to get there, to do this pivoting? N time, right? I have to, yeah. Good. Exactly, right? So if we can luckily manage to recurse on only one side and it's only 3/4 n, what did we learn from the recurrence? Yeah, if we can cut down the size of the problem by constant factor, even though we spend linear time, the total time will be linear. Right? If you can get a recurrence of the form T of n is 3Tn/4 plus n, what is the solution to the recurrence? Constant times n, right? Because it's a geometric series. So if you spend n time and cut down the problem size by a constant factor, we'll be done, right? But we don't have control over the pivot, no? What's the bad case for quicksort? Yeah, so the bad case is the array is already sorted and I'm looking for the last element. What will you do? Yeah? We will find the first element and we have to recurse in an array of size n-1, right? So T of n will be n plus T of n-1. It's better to sort than do that, no? It's like, oh, what have we gained from this? Okay, but what we have gained is that if you somehow can magically ensure that the pivot is a good pivot, we can actually get linear running time. Yeah? So, okay, so knowing that information, now we have to look for a magical way to get that pivot. So what is magic here? We don't have any magic bullet, no? One way to do it easily is to pick a random pivot. If you pick a random pivot, what's good about a random pivot? Yeah? Oh, it's random, so what does it mean, right? It's going to be anywhere, but with a half probability, it will be somewhere in the middle. Okay? And that's good enough. In fact, that's the most practical algorithm if you want to implement. Okay? You pick a random pivot. Okay? It's in expected linear time, you'll do it. But we are not in randomized world yet, right? That's too advanced for now. So we are still in the deterministic world, but we want to find this good pivot. How are we going to do it? So some brilliant people had a very good idea. And again, recursion to the rescue, okay? So but the important thing is to realize that we need to find a good pivot. And we have to do it fast, right? If you spend a lot of time finding a good pivot, then we are not going to be in good shape. So we want to get a recurrence like this, right? By finding a good pivot. So how do we find it? Okay, yeah, randomly works. Here is a very strange but cute idea, right? So let me explain it by a figure. So I want to find a good pivot for it. What is a good pivot? It splits the array roughly in the middle, right? Okay, how do I get my hand on that, right? So this is what these guys suggested, right? They said, break the array up into a two-dimensional array, okay, like this. I'm going to do it with three, but I will. Okay, so they said, okay, take this long array and group them into 5 elements each. So how many groups will you get if you break them into 5 elements each? N over 5, right? So we take this long array and break them into groups of 5 each. Now within each group we find the median of them. Is it easy? 5 elements, it's easy, no? How long will it take to find the median of 5 elements? Do whatever you want, brute force, right? It will take some constant time, right? Something which depends on 5, but say 5 log 5, right? Yeah? Okay, so what is the total work we do to find the median in each group? Some n times some constant, right? Yeah? Okay, so now, I did that. So instead of doing it for 5 because it is too long of an array, let's do it for 3 groups of size 3. Yeah? So 11, 7, 3, 42, 174, 310, 192, 87, 12, 19, 15, right? Okay. Now what is the median of these 3 numbers? Okay, 7, I write it down. What is the median of these 3 numbers? Sorry? 174. What is the median of these 3 numbers? 87. What is the median of these 3 numbers? Sorry? 15, right? Okay. How many numbers do I have here? If the original array is of size n, how many numbers do I have here? N over 3, right? Okay, but if I have 5, how many numbers will I get? N over 5. Now my claim is the median of those n over 5 numbers is a good median for the entire array. Okay. The statement is, if I take the median of this, what is the median of this? Well, it is 15, right? Okay, if I can find the median of this and I use that as a pivot in this array, that will split the array roughly equally. Okay, I have to prove that to you. Okay? Okay? So have you done anything interesting? Okay, I claim you have done something interesting. Okay, why is this a smaller problem? Yeah? Yeah? No, but I'm saying why is this a smaller problem? Because there are only how many numbers here? N by 3, no? Or n by 5 if I use 5, right? So, there are 2 claims I'm making. First, to compute these medians takes only n time, right? I mean, these individual 5 medians of each of those, right? So, how much work have you done to create this list? Only n time, right? But what is the size of this list? If I use groups of size 5, n over 5, right? Okay, I claim without proof yet that if you find the median of this, then that is an approximately good median which splits the array nicely for the entire array. Okay? But what is the advantage? How do I find the median of this? I don't have anything else, but I just recurse. Okay? Does it make sense? Okay. I don't know how to find the median other than solving recursively the median of this by just using the same algorithm, but the only advantage is that the size of this list is what? Less, right? Now you may say, okay, wait a second. You are telling me to split this array nicely, you have to do all this work, create this smaller list, find the median recursively, then go back to this, split this, and then recurse again. Wait, why do you think that will be in linear time? Okay, but if you do the algebra, it works out. Okay? Okay? That is the idea of sticking with a thought. Okay? Okay, you have to stick with the thought and let the algebra guide you, right? So it works. Okay, that is the idea. So is the algorithm clear? Okay, what is the algorithm? You first, I'm doing it with 3 because it's hard to do it with 5. So you start with this array, you create groups of 5, and then find the median in each small group. Yeah? Create a list of the medians, so it's a median of medians. Find the median of this recursively. Okay? That will give you what? A number, right? And use that as a pivot to split this. Okay? And then look for one, then select for the either left side or right side like we did it before. Is it okay? Okay, here is the algorithm. Why? Yes, good idea. So I'll tell you why they did this, okay? So let's understand the algorithm. The algorithm is this, right? Let's see, here is the algorithm. Select, what are we trying to solve? We are find the jth ranked element in an array of size n, right? Okay? So that is this algorithm. What do you do first step? You form this lists of 5 elements each, right? Yeah? So there are, how many lists are there? N over 5, right? Don't worry about divisibility by 5, right? Yeah. And now what do? You find the median of each of those lists, right? B1, B2, Bn over 5. Yeah? Okay, then what do we find? We have to find the median of all those B1, B2, Bn over 5, right? Yeah? And then once you find that median, we use it as a pivot to split A into A less and A greater than. And we do the obvious thing we did. If the rank of the element we want of the pivot is exactly j, we are done, right? We found it. Otherwise, we recurse on the left or the recurse on the right as we did before. Yeah? Okay? This looks bizarre, no? Okay? Is the algorithm clear? Okay, but we don't know how to find the median here, right? Without recursing. So we actually, this is the algorithm. B is now what? Yeah. You again do a recursive call, but what rank should we use? The median, right? So the rank is n over 10, right? Because we are now an array of size n over 5. What is the median rank? It's n over 10 roughly. Yeah? Okay? Okay, is the algorithm clear? Let's not worry about that, right? Okay? Okay? Yeah? It's a strange algorithm, no? Okay, so how do we write a recurrence for this? Okay? How many calls are we making? 2 calls, right? Okay? One to a problem of size what? N over 5, right? This is n over 5, right? This array B is of size n over 5. And then, do we know the size of A less and A greater? We don't know it, right? How do we know where is the pivot? Okay, that is a technical theorem. Here is the thing. The claim is that the pivot is good. Okay, what does it mean the pivot is good? That the median of the medians has the property that both A less and A greater are less than 7 and over 10. Okay, believe me for now. Don't worry about this plus 6. That means that the pivot of the median of the medians is not going to split the array in a lopsided fashion. It will a little bit, but not too bad. What is not too bad? It is guaranteed that both sides are less than 7 and over 10. I don't know what it will do, but I'm guaranteed that I won't get n minus 1 and 1, right? It's not going to be in the middle, exactly in the middle, but it will guarantee that it is somewhere in the middle. Okay? What is somewhere in the middle? This is the quantification. That I'm guaranteed that both the left hand side and the right hand side are no more than 7n over 10. Okay? This is a mathematical fact. I have not computational fact, right? Okay? Is it clear that it's a mathematical fact that the median of the medians satisfies this property? Okay? Assuming this property, can we write a recurrence now for this algorithm? Okay? Yes, you can, right? Why not, right? See, I claim T of n is less than T of n over 5, right? Because I'm making a call for n over 5 elements, right? That's the call to find the median of the medians. But I don't know whether I have to recurse on the left hand side or right hand side, right? Okay? But I can make this, right? Whatever is the maximum size of the left hand side and right hand side is an upper bound, right? On the size of the problem I'm recursing on. But how much time did I spend to do this? Well, I made these 2 recursive calls. I had to compute the medians. That is n time, right? I have to spend n time on that. So are you okay with this recurrence for that code? No? Can I ask me questions? Sorry? Oh, this makes sense because what do we do, right? We first compute arrays of size 5 and compute the median in each of them, right? That takes constant time. So this time to compute B is only n time. Then we make one call to the recursive call on an array of size what? b1 to bn over 5, right? So that is only tn over 5. That's one recursive call. And then we use that pivot, the median to pivot. That takes n time. And then we call on either left or right, right? So I don't know which one I'm going to recurse on, but the maximum size is what I can put here. Yeah? Oh, 5n, okay. Well, because, it depends. This is a computation to do this and computation to do pivoting, no? I don't know how much exactly, but it is some constant times. Okay, but from the mathematical theorem, you will get the statement that it is T of n is T of n over 5 plus what is the biggest size we can get? It is at most 7n over 10. You say, aha, what is this? And the answer is linear. And we are done. Okay, we are not done. We haven't proved it to you, right? But that is the idea, right? The idea is that if we can cut the problem down by a constant factor, even if you make 2 recursive calls, you will still get linear time. Because the sum of n over 5 plus 7n over 10 is still a constant factor less than n. Okay? Okay, that's the beauty of this. See, but we need to know recurrences to develop this algorithm. And to just tell you why this is not obvious, you know who these guys are? Okay, this paper was written by Manuel Blum, Bob Floyd, Donald Knuth, Von Pratt, Ron Rivest, and Robert Tarjan. Okay? All of them except Von Pratt are Turing Award winners. Okay? All of them except Von Pratt are Turing Award winners. Okay? Yeah, they're the best, the Nobel Prize in computer science. Okay? So this simple problem, right, was solved by these amazing people, right? It's very simple. Yeah.
So for this one, so the size, the width increases like by 1, 2, 4, 8, 16.